All right, chapter 17 is on solubility of ionic compounds. Recall from chapter 4 in Gen Chem 1 that a compound can be considered soluble if it dissolves completely in water, and it is considered insoluble if it doesn't. So if you have floaties, if you take two test tubes, let's say, and those are clear, and you mix them together and it generates solid within the mass, we say that it's an insoluble precipitate that has been generated, and we call that reaction precipitation reaction. On the other hand, if everything still remains soluble, then and it's a clear solution that you have at the end of the day, then you say then that particular salt is it dissolves in water, it's soluble. So recall that we went over several solubility rules and we classified ionic compounds basically as soluble and insoluble salts. Um, Now, in this particular chapter, we are going to take that one step forward, one step deeper. We would be able to utilize the concept of equilibrium to understand, or I should say, better understand the solubility of an ionic compound. So we would be able to define the degrees of solubility. The degrees of solubility. How soluble? If it is soluble, how soluble is it? If it is insoluble, how insoluble it is. So the process of dissolution would be better understood in this case. Now, we have seen several equilibrium constants since the time we started with chapter 14, Kc, Kp, Kw, Kn, Ka, Kb. In this particular chapter, we are going to talk about what is called as the solubility product constant, or KSP. So we are considering an equation, calcium fluoride, CaF2, which is a solid and it's in equilibrium with Ca2 plus 2F negative. So we have represented the dissolution of calcium fluoride in water in the form of this equilibrium equation. Now, the equilibrium expression for this equilibrium equation, it can be represented, like I said, with the constant KSP, and hopefully you can see that it's only the products that are going to participate. The reactant, the fact that it is a solid is not going to participate in the equilibrium, but you can write down your KSP as Ca2 plus times the concentration of fluoride, and you will need to take a square of that. So let me, because all of my formatting is lost in between going from PC to a Mac, it's going to look like Ca2 plus F minus and square of that, and that will give you KSP. Now, the value of the KSP that you get is the measure of the solubility of the compound. So higher is this value, we would say that that particular compound is very soluble in nature. And if you have numbers to the tune of like 10 to the power of minus 10, 10 to the power of negative 30, and things of that nature, then you would be able to tell that you don't have as many products in the system. That particular salt primarily stays as the solid, and hence you would call that the insoluble solid in that case. Now, let's see if we are able to write some KSP expressions for the following. So you're given 4 different compounds. You have to write down the KSP expression. So hopefully you realize that in order to do that, you first will need to write down the equilibrium. MgOH is a solid that is going to give you Mg2 plus 2 hydroxides. And so your KSP should look like the concentration of magnesium times the concentration of hydroxide, and you'll take a square of that. If you had to do that for strontium carbonate, you will say that's going to give you SR2 plus carbonate 2 negative. And so the KSP is going to look like strontium times carbonate. If you look at calcium arsenate, that's going to give you 3 calciums plus 2 arsenates. So your KSP will look like calcium raised to the power of 3, arsenate raised to the power of 2. Iron hydroxide, Fe3 plus 3 hydroxides. The KSP is going to be equal to Fe times hydroxide raised to the power of 3. Okay, now that we have a better handle on the KSP, which is the equilibrium constant, let's talk about solubility. We've seen solubility previously in chapter 12, where we discussed that solubility of a compound is the quantity of the compound that dissolves in a certain amount of liquid. So solubility is the quantity of a compound that dissolves in a certain amount of liquid. So if you're saying that, let's say there is sodium chloride in water and I have 30 grams that dissolved in 50 milliliters at a certain temperature, you'll have to specify the temperature, you'll have to specify the amount. So the grams per 50 milliliter, of course, you'll write that as liters, but at that particular temperature will be called as the solubility. And the molar solubility is the solubility in units of moles per liter. So let's take a look if we are given some information on solubility and if we can determine how we can correlate the KSP from here. The question is, the solubility of silver bromate, AgBrO3, in water is 0.0072 grams per liter. We have to calculate the KSP. So we have our equilibrium, first of all, AgBrO3, which is a solid. You put an equilibrium. It is in equilibrium with silver, aqueous, plus bromate, which is also aqueous. And we have to determine KSP. KSP, as you can see, is concentration of silver times concentration of bromate. So if you had the molar concentration of Ag plus and BrO3 minus, you can substitute that and you can get KSP. So the question is, what is the link between the molar concentration and solubility? Realize what I said a couple minutes ago. I said solubility is the quantity of a compound that dissolves in a certain amount of liquid. That means for any solution, you can have various different solubilities, because as you change the reaction conditions or as you change the physical constants such as temperature, it's going to have a different solubility. Or let's say you had a solubility in pure water, and now if you have a certain ion already present, then due to common ion effect you can have a decreased solubility for that matter. So realize solubility, or in other words, the concentration that you have in here is going to be dependent on your physical parameters. But the KSP that you have, that is not the molar solubility. It is the solubility product constant, and that will have only one value at a given temperature. It's not going to change, okay? So, again, realize the solubility can vary. Solubility product is going to be constant at a given temperature. Now, I also mentioned solubility and molar solubility. Solubility is in grams per liter, whereas molar solubility will be in units of moles per liter. So it's like a molar concentration. So hopefully you can see that for this AgBrO3 system, if you had to set up an ice where initial concentration, of course, we have no silver and no bromate in the system, and let's say the equilibrium or by equilibrium, the change that occurs gives you S moles of, S for solubility, S moles of silver and S of bromate, then at equilibrium you're going to end up with, and the equilibrium is just a summation of I and C part. We know that for 3 chapters now. So hopefully you are able to see that the solubility of any partly soluble or insoluble salt is directly related by the reaction stoichiometry to the amounts of the ions that it is made up of, and this is when equilibrium has been reached. And so consequently, finding molar solubility from KSP, or if you're given molar solubility, determine KSP, that's only a logical thing to do. So I represented this as S, and hopefully we can see that the KSP is going to be equal to, if I plug in the numbers, S times S, which will be S squared. Now the question is, what is S, or is there any piece of information that can be converted into something which is useful or more useful than what it is right now? Realize my solubility is given as 0.0072 grams per liter. And I said that molar solubility has got to be in moles per liter. So in order to do that, I will need to convert the grams into moles. That means for silver, I'm going to need the molar mass for this. So for silver, I'm going to need 108. Bromine is 80. Oxygen is 16, so 3 times 16, that's 48. So 48 plus 80 plus 108, and that gives you, so that's 236 grams per mole. And so I can put that 236 grams per mole to convert the grams per liter into moles per liter. So that's going to look like 0.0072 divided by 236. That's a 3.05 times 10 to the negative fifth. That's 3.05 times 10 to the negative fifth. And this is the moles per liter. And this is also going to be the molar concentration at equilibrium. So that's the value of S basically. So I'm going to say that 3.05 times 10 to the negative fifth, and we square that. So that's going to be roughly 9 times, but I'm still going to put the number just for the sake of argument, 9.31 times 10 to the negative 10. This is going to be your KSP. All right, let's go forward. Let's take a look at another question. The question is that we have to again calculate the KSP of copper 2 iodate. The formula is provided to you. The solubility, 1L only, of copper 2 iodate and water is 0.13 for 100 milliliters. So hopefully you can see that it's going to be 1.3 for 1,000 milliliter, or you can just write it as 1.3 grams per liter, because we will need to convert it into moles per liter at some point of time. The equation we are talking about is CuIO3 twice, and that means the equilibrium is this iodate. Both of the charges are aqueous. This guy is solid. Let's first calculate the molar mass. So copper is 63.5. Iodine is 126. So 2 times 126, 6 times 16. So this is 96. This is 252. Or is it 127? I think it's 126.9, so 127. So 254. And now we're going to simply add those. And that comes out to be 413.5 grams per mole. And you have to convert the solubility into molar solubility first. So again, 1.3 grams per liter. And since this is 413 grams per mole, you would say 1.3, divide that number by 413.5, and that will give you 3.14 times 10 to the power of minus 3 moles per liter. That's going to be your molar solubility. And we are going to use that, the molar solubility, we are going to use that for getting our KSP value. So let's set up the ice to see how it's going to look. We can hopefully see that KSP is going to be equal to the concentration of copper plus concentration of iodate, and we are going to take the square of the iodate. Now setting up the ice, copper is going to be S, initially copper is going to be 0, and so would be the iodate. If the change is by X, then that would mean that you have S moles of copper, and you have 2 S moles of the iodate. And so at equilibrium, these are the numbers. So if we now plug those back into the KSP, it's going to look like S times 2S, square of that, and that's your KSP. That means 4S cubed will be KSP. And the molar solubility is given. So 4 times 3.14 times 10 to the negative 3 cube of that is going to be your KSP. And let's solve that now. And that boils down to 1.2 times 10 to the negative 7 as your overall KSP. Let's, for the sake of argument, work on the other way around. That means you're given the KSP and you have to determine the molar solubility. So let's see. The question is calculate the molar solubility of PbCl2 in pure water. So first things first, you should write down the equilibrium PbCl2 in solid in equilibrium with Pb2 plus and 2 chlorides as the aqueous. KSP is Pb2 plus and Cl negative, square of that. And so you will have to set up the ice again. So hopefully you can see that in the beginning there would be no PB. If the change is by S, chloride is going to be twice the amount. And so at equilibrium, this guy is going to be S, this is going to be 2S. And so if you're putting your numbers for your KSP, that will be S times 2S square of that, which is 4S cubed, should be equal to, I have a table in the book, so which has all of these KSP values, and in that I'm seeking PB chloride. So lead 2 chloride is 1.17 times 10 to the negative fifth. And so now we basically solve for the solubility. So solubility is going to be equal to cube root of 1.17 times 10 to the negative fifth over 4. So those are two steps again. I divided both sides of the equation by 4 first, and then I took a cube root, because it's a cube, so I took a cube root of that, and that number comes out to be 1.43 times 10 to the power of negative 2 molar. So that's your molar solubility or molar concentration at equilibrium. Two ways to say the same thing. We have seen that the molar solubility and the KSP are related, and each can be calculated from each other. I've spent good amount of time just going over that. But realize that you cannot generally use the KSP values of two different compounds to directly compare to each other. I mean, a couple minutes ago in one of the slides, I think I made a statement that higher is the KSP, if that's a positive value, then we can say that that particular compound is soluble. Yes, I said that with respect to the law of mass action based on the equilibrium that you know, that if you have a higher value, let's say 10 to the power of 4, that means essentially the equilibrium is lying more towards the product side. So in that sense, but you can't just compare. Let's say you have two different salts. Let me pull two numbers from this table. Magnesium hydroxide, it has a KSP of 2.06 times 10 to the power of minus 13, and the solubility is 3.72 times 10 to the negative fifth. And iron carbonate, that has a KSP of 3.07 times 10 to the negative 11, and the solubility is only 5.54 times 10 to the negative 6. So what we are saying is that the KSP of iron carbonate is higher, but somehow its solubility is lower. So magnesium hydroxide has a smaller KSP than iron 2 carbonate, but it has a higher molar solubility. So the two don't kind of go hand in hand. The reason for that in this case is that the relationship between the KSP and the molar solubility depends on the stoichiometry of the dissociation reaction also. Realize, in case of magnesium hydroxide, you're going to get S moles of magnesium and 2S of the hydroxide. So overall, your KSP is going to look like 4S cubed for magnesium hydroxide. On the other hand, FeCO3 is going to look like just one iron, one carbonate. That means X squared is going to be equal to KSP. So, or S squared is going to be your KSP. So the value of S, the way you calculate, is going to be different. You can't really quite compare in between two salts. So it's a very sort of within the salt type of a scenario when I first said it's in accordance with the law of mass action that we were talking about. So any direct comparison of KSP values for two different compounds, that means if you wanted to compare magnesium hydroxide to something else, well, pick something like strontium hydroxide or calcium hydroxide, because you know that the stoichiometry is going to be exactly the same, and so you would be looking at a 4s cube type of a format. In both of those cases, you would be able to compare the apples to apples, not apples to oranges in that case. So realize, something like magnesium hydroxide, calcium fluoride, those can be compared. Magnesium hydroxide, calcium hydroxide, those can be compared as well, because they're going to give you 1 mole of each compound upon dissociation will give you overall 3 moles of the dissolved ions. And so the KSP values will be directly compared as a direct measure of their relative solubilities.